Okay, so today's lesson is section 7.7 from the Sullivan book on the graphs of tangent, cotangent, cosecant, secant, and today's focus will be specifically on tangent and cotangent. So you'll see that in the objective. It says I can graph the tangent and cotangent functions. So we're going to start off by graphing y equals tangent of x using a table of values on the interval from negative pi over 2 to pi over 2. So I know that usually when we make a table we focused on positive values only for x, but I did want to show you something a little unique that happens with tangent if I do include some negative values. So just remember, if you could get out your unit circle, when we're trying to locate these negative values, you're just going in the negative direction around the unit circle, but that same amount of space you would if you were going in the positive direction to that angle. So negative pi over 2 is actually at the same location as like your positive 270 degrees or positive 3 pi over 2. And if you notice at that spot, something that you'll have to remember is that tangent of x would be equal to the sine of x over the cosine of x, depending on whatever that x angle represents. So you're going to see that tangent of x is undefined. Defined whenever cosine of x equals 0. So if you look at your unit circle, cosine being our x values, where are our x values? 0. Well, you're noticing that that's going to happen here at pi over 2 and here at 3 pi over 2, which is the same thing as negative pi over 2. So what I'd like to write in these spots here is just undefined. And remember, when a graph is undefined, there's two different ways we've seen that represented at this point. We've seen open holes in a graph or open circles, and then we've also seen dashed lines that represent asymptotes. So asymptotes is going to be the way we go today. If you go to negative pi over 4, that would be going in the negative direction 45 degrees, which would actually land you here at the same spot as positive 7 pi over 4. And if tangent is y over x, if I divide negative square root of 2 over 2 by square root of 2 over 2, I would get negative 1. If I go to 0, again, tangent being y over x, I would get 0 over 1, which is 0. Positive pi over 4, I'm noticing my y and my x are the same value, so when I divide them, I get 1. And then I'm going to run into another issue when I hit pi over 2, because I'm going to try to divide 1 by 0, and it will be undefined. So any spot where I see cosine of x equaling 0, that's going to be where I run into an asymptote. So I'm going to go ahead and try to graph this. I know there's not a whole lot of points there, but I want to show you how this starts to form. Tangent is periodic, similar to sine and cosine, so you are going to see repetition once we start to see the pattern. So we can go ahead and get our graph started. This is going to serve as like your parent graph for the tangent function. I'm going to try to space this out a little bit like we have on our other graphs. I'm going to start by labeling this the same way that we did all of our parent graphs, by counting by pi over 2 or 1/2 pi. So now if I plot those values, at negative pi over 2, I found out that tangent of x is undefined. So I'm going to represent that with a vertical asymptote. I find out that at negative pi over 4, I get an output of negative 1. Negative pi over 4 is going to be halfway in between 0 and negative pi over 2. So it'd be down here. I would get a point. At 0, I get 0. Positive pi over 4, I'm at 1. And at pi over 2, I have another vertical asymptote to represent that it is undefined. The way that you draw any tangent function, and if you want to take a look at your book, they do find more values in between those two asymptotes to start to show you how the curve is formed. But you do see a curve that looks very similar to a cubic. It does continue up and continue down. If you remember back to our range for a tangent function, it was all real numbers, and then the domain was limited based on where I ended up seeing these vertical asymptotes. So you are going to see repetition here. If you think about going around the unit circle and talking about tangent, you are going to see another undefined value at 3 pi over 2. Because 3 pi over 2, you get the same tangent value as you would at negative pi over 2. So I'm going to go ahead and draw in another asymptote. You could look at your circle if you're not sure about what I'm talking about. Look at 3 pi over 2, and I can show you really quick. You're going to see that the x value there is 0, and that means that y divided by x, or tangent, would be undefined. At positive pi, you are going to see that you would get x over y, or 0 divided by negative 1, which would be 0. So you're going to see a lot of repetition here, and again, you could make a larger table if you'd like, but you are going to see these repetitive points. So again, halfway between these two spots, I'm going to have a point up here at a y value of 1, down here at negative 1, and again this curve. So what I would like to see from you guys when it comes to graphing tangent is at least 2 of these curves. I am going to draw one more just to try to be a little consistent on the left side. So I'll probably usually draw 3 of these when I graph. So that'd be a total of 4 asymptotes. But that's going to be your parent graph for tangent. So I want to go ahead and give you a list of some properties that I would like for you to copy into your notes. So I'm going to go ahead and project these real quickly if you want to go ahead and pause the video so you can get them written down. Okay, I can read through them quickly. The domain is the set of all real numbers except odd multiples of pi over 2. Remember, this is going to pertain to our parent graph only. If we have some kind of stretch or compression happening, your asymptotes may have to be relocated. The range is all real numbers. You can see from the graph with the arrows heading up and down that there's no limit to our y values. This graph would be considered to be odd. You'll notice I have one end up, one end down. Also, it has symmetry with respect to the origin, the same way you see with a sine graph. It is periodic with a period of pi, so you're going to see repetition every 0 to pi. There are x-intercepts. You see some of them listed there. Your y-intercept is at 0, and you do have vertical asymptotes at every 1/2 pi or 3/2 pi, and intervals coinciding with that. So go ahead and take a minute. Again, if you need to, pause the video so you can get that copied down. And we're going to go ahead and move on and do some practice now with graphing tangent other than just the parent graph. So if you take a look with me at example 1, notice a couple things are happening to that equation. You're going to see the 2 out in front, which we usually refer to as a vertical stretch, which means you have to multiply your y values by 2. And then you'll see that -1 in the back, which means the graph would have to be shifted down 1. I do have a little tip to give you before we start graphing, and it relates to our stretches, compressions, and things like that. And if you would add this to your notes, please. If I have a function at f of x equals A times the tangent of BX. So A would be similar to the idea of an amplitude of a sine or cosine function, but we really don't say that tangent has an amplitude because it doesn't have like this rise and fall like a sine and cosine graph does, but it does have that same kind of relationship where it's the distance between like that middle point and my above and below points. And then that B value would be similar to what we saw as omega yesterday, but that's going to cause your horizontal stretch or compression. And some things to keep in mind is that the period of tangent is pi. So if we're talking about figuring out a period for a graph that has a stretch or compression, you're going to want to take pi, not 2 pi, but just pi because we're talking about tangent, and divide it by the absolute value of B. So similar to what we did yesterday with omega, but just notice that you're not going to want to worry about if it's negative. You want to just always use a positive value, and our period will be represented as a positive. And then you also would know where your asymptotes are located. And that would be at your negative period divided by 2, and the positive value you get for P divided by 2. And then you would just count by that value and extend it to the left and the right to continue your asymptote. So this would kind of be like almost like your cheat sheet for graphing tangent. Find the period, find the location of your asymptotes, and then you'll know how to count your axis, and then your kind of zeros or middle values will be in between those asymptotes. Let me show you what I mean as we graph example 1. If I want to graph y equals 2 times tangent of x minus 1, start by finding out what A is. A would equal 2, and again that's going to be similar to this idea of an amplitude, and I'll show you how that comes into play in our graph. When I want to find the period, I would do pi divided by the absolute value of B. B would come from what's right here in front of this x, and notice in this problem it's just a 1. So our period would just be pi, that's standard of value for tangent. And then that means that for this graph I would have asymptotes at negative pi over 2 and pi over 2, which is just that standard parent graph. So the biggest change that's going to happen to this graph from the parent graph is that space between that middle value and kind of that right and left point will be 2 instead of 1, and then I'm going to shift my whole graph down 1 because of that minus 1. Okay, so if I go ahead and get my graph started, I'm not going to make it mandatory that you draw parent graphs for these because I feel like you'll get the hang of it once I show you this first example. Again, I'm going to use wherever my asymptotes are located as what I'm going to count my axis by. So I am going to count by pi over 2, so that'd be 1 pi over 2, 2 pi over 2 would be pi, 3 pi over 2, and then 4 pi over 2 would land me at 2 pi. So again, this is going to have that same layout that we're comfortable with from our parent graphs. I'm going to always start my tangent graphs out by graphing my asymptotes. So I'm going to start here. And you'll have an asymptote at every other spot following that pattern. I'm still going to have my points, well at least my parent graph would have started here at 0, 0, but I did have a shift down 1, so it'll land me here at -1 instead. If I was looking at the parent graph, I had a space of 1 in between the point that was up and to the right of this center point, because of that a value of 2, instead of going up 1 and over 1, I would go up 2 and over 1. And I would have the same kind of thing happen below. So 1, I would need to make another little mark here. 2. So you're going to see that it looks a little bit vertically stretched. And again, it also looks like it's been shifted down. What's nice about this is, again, it's very repetitive or periodic. So I should be able to sketch this in from there. And I might need to extend my asymptotes a little bit because I don't want that to be misrepresented. And there would be our graph. Okay, so let me go ahead and move on to the next example. Example 2. Again, we're going to see a vertical and then a horizontal as well, stretch or compression. So we'll see how that plays out kind of using that little setup that I gave you a few minutes ago. I would go ahead and write down that A is 3, so we'll want to make sure we space out our points accordingly. To find our period, again for tangent, we're always going to start out with pi, and then in this case we'll divide by 2. So our period in this problem is pi over 2, which means when we go to find our asymptotes, I'm going to have to do negative pi over 2 divided by 2 and pi over 2 divided by 2. Which would be negative pi over 2 times 1 over 2, or negative pi over 4. And this would be positive pi over 4. So I'm going to go ahead and get my graph started by counting by pi over 4s on my axis. So instead of counting by pi over 2 this time, I am going to count by pi over 4. So it's easy to locate my asymptotes. And I'm going to need a little bit more space here, so I'm going to count 1, 2, 3 and just use one box. So this would be 1 pi over 4, 2 pi over 4 would reduce to pi over 2, 3 pi over 4, and 4 pi over 4 would be pi. And then I repeat those values on the negative side. Okay, draw in my asymptotes. So pi over 4, I'd have an asymptote. And again, you're just going to want to skip every other one, like we've done on the last graph. So the thing I want to show you is that I kind of gave you these tips on how to find the period, how to find the location of the asymptotes, but really what we're doing when we do this problem is we're asking ourselves, where is cosine 0? Because wherever cosine in this particular function is 0, that's where you're going to see undefined. So if I go back up to the equation, this was 3 times tangent of 2x. What we're really looking for where 3 times cosine of 2x would be 0. And those are going to be our undefined values. So just keep in mind whenever we're working with tangent that we're looking for where cosine is 0, and that's where we're landing our asymptotes. So there's no up or down shift to this equation. What I'm going to have to do here is still then start at 0, 0, but instead of just going up 1 and over 1, I would go like up 3 and over 1. And then you would just continue that pattern. So this is pretty simple as long as you understand how to place your asymptotes, and then everything else gets spaced kind of evenly in between. You would just need to be careful about that A value, helping you understand how to space things out. The other thing I want to mention is when you might see the graph rise to the left and go down to the right instead of rising right and going down to the left. And that's going to be when you have some kind of reflection. So you want to kind of watch out for that. That would be when you have a negative in front of the tangent, and then you'll see that reflection. Whether you reflect it over the x or the y, it is going to look the same, just like I was trying to explain to you about sine. Now, cotangent also looks that way, but cotangent's asymptotes are in different places. And I want to go ahead and use our parent graph for tangent to show you what the graph for cotangent would be. I don't really plan on having you graph a whole lot when it comes to cotangent, but I do want to show you how we can develop it. So our next example, example 3, is going to ask you to graph y equals cotangent of x. But to get there, I want to show you a little bit on our parent graph of just tangent of x. So if you kind of want to look back to your notes or just take a look at what I have up here. This was our parent graph for tangent. What you have to understand is there's going to be kind of this flip-flop between tangent and cotangent of where it's undefined and where it's 0. So if you think about it, I can even make notes up here. Tangent of x is sine over cosine. So cotangent of x would be cosine over sine. So the spots where here I had 1 over 0, making it undefined, I now would have 0 over 1, and that's not undefined anymore, it's 0. So I'm going to use my highlighter to kind of show you what's going to happen. But where I had asymptotes before,